In this video, we're going to introduce power series. One primary reason for studying studying series in general is to be able to approximate functions using polynomials. Polynomials are exceptionally nice functions for us, right? Because really all you're doing is adding. Multiplication is adding fast, subtraction is adding backwards, exponentiation is just multiplying fast, so that's adding really fast. Polynomials are literally just adding. That's all we do. But the nice thing about polynomials is that, of course, they're continuous everywhere, they're differentiable everywhere, they're just really, really nice functions to work with. So if we can approximate weird functions with polynomials and then do the analysis on the polynomials, that just makes life a little bit easier. So to help us out with this approximation, we introduced the concept of power series. So a power series, in some respects, looks like an infinitely long polynomial. We have a series starting at 0 going to infinity. We have coefficients, and we've got powers of x. Now, in this case, it says it's centered at a. So this is basically kind of a shift by a units, depending left or right, depending on the value of a. But this is like an infinite polynomial in x, right? We've got an x to the 0 power, an x to the first power, an x to the second power, and so on down the line. So that's what we mean by a power series. A lot of the series that we'll deal with tend to be centered at 0. So if it's centered at 0, if our a is 0, then we just really do get this thing that looks like an infinitely long polynomial. If we don't specify a center and we say the word power series, we're going to assume that we really do mean that it's centered at 0. Now, one other thing to note is that if I take x minus a and raise it to the 0 power, I'm going to assume that I get 1. Even if the thing that I'm raising to the 0 power is 0. Technically speaking, 0 to the 0 is undefined. However, if we have the limit as x goes to 0 of x to the x, that turns out to be 1. Okay? So our convention will be to assume that we've got 0 to the 0 as 1 in this case, because that's how the limit would behave for that constant term. All right, again, we want to use power series as approximation tools. To be able to make sure that we can approximate using a power series, it's important to know when this power series converges. For what values can we plug in for x and get a convergent series? Otherwise, the approximation is not going to be very helpful to us if the sum's going to go off to infinity. All right, so as an example here, let's look at what values of x have this series from 1 to infinity of x plus 1 to the n over square root of n. What does that converge for? Now, from the ratio test and the root test section, those two tests have a nice condition for when a series is convergent and when a series is divergent, right? We look at the limit, and if the limit was less than 1, it converged. If the limit was absolutely convergent. If the limit was greater than 1, it diverged. So we've got that nice little condition that tells us whether or not the series converges if we can go through and compute the limit. So to that end, let's use the ratio test here. Limit of the absolute value of the ratio of consecutive terms. We get on top x plus 1 to the n plus 1 over square root of n plus 1 over x plus 1 to the n over root n. Let's do some simplifying. N is positive here, so root n and root n plus 1 are positive. So we could pull those outside of the absolute value signs. Inside, though, x could be bigger than -1, could be less than -1, we don't know. So it's certain that that value could be negative, so we need the absolute value bars on there. However, we can simplify and get just x plus 1 to the first power. And then I can rewrite this as square root of n over n plus 1. Now I want to do a limit. Well, there aren't any n's in here, so we're going to assume that x is fixed. It might be an arbitrary x value, but assuming that it's fixed for the limit purposes, this limit is 1. So we just get absolute value of x plus 1 for our limit. The ratio test says that if the limit turns out to be less than 1, then the series will converge. So the limit here is absolute value of x plus 1. So in order for the power series to converge, we need absolute value of x plus 1 to be less than 1. So this tells us that the series will converge if x is between 0 and -2. And it will diverge if our x is less than -2 or greater than 0. So that tells us that the series converges if the value that we plug in for x is within 1 unit of -1. And -1 here was our center of our power series. So the fact that anything that's within a unit of 1 will make it converge. We refer to that as our radius of convergence for the power series. Now, if we actually plug in 0 or plug into -2, the limit is 1, so the ratio test is inconclusive. And this happens in a lot of problems. If you get a radius of convergence that's a value between that's bigger than 0 but less than infinity, we're going to have endpoints that we'll have to check. Okay. So if we put in -2 for x, we get -1 to the n over root n. That's an alternating series. The terms go to 0 and they decrease all the time. So we get a convergent alternating series. If x is equal to 0, when we plug in 0, we'll just get 1 over root n, because 1 to the n is always 1. That's 1 over n to the 1/2. That's a divergent p-series. So the series will converge on the interval -2 included, 0 excluded. So any x that we pick from that interval, the series will converge if we plug it in. We refer to that as the interval of convergence for the series. All right, so for a power series, when we're doing these convergence ideas, we're really going to have an interval of convergence that's centered at the center. There's going to be only 3 possibilities for that to happen. All right, so let's talk about it. The series converges only when x equals a. That's one possibility. Certainly, the series will always converge if you put in a, because you get all of the terms except for the constant term to be 0. And we said by convention the constant term will be c sub 0, because 0 to the 0 will be 1. So no matter what, a power series always converges as its center, but that may be the only place where it converges, and that's not very helpful. In that case, the radius of convergence is 0, and the interval of convergence is not really an interval, it's just a single point, a. The other extreme is that the series will converge no matter what we plug in for x. Those are great series. The radius of convergence in that case is infinity. And the interval of convergence, of course, will be all real numbers. For all intents and purposes, it's the third case that pops up the most often. We get an interval of values where if the x value is in the interval, it converges. If the x value is outside the interval, it diverges. Or within that radius and outside that radius, I guess I should say. We call that the radius of convergence, in that case, that value for r, and that was what we saw in the previous example with 1 for the radius of convergence. All right, notice in the third case when we have a number that gives us the radius of convergence, there's 4 possible intervals of convergence. Because again, we don't know just by knowing the radius that it converges at the endpoint. That was what we saw in that previous example, where it converged when x was equal to -2, but diverged when x was equal to 0. Okay. So the 4 possibilities are: it converges at neither endpoint, it converges at the left endpoint but not the right, at the right but not the left, or at both. So in all of these cases, when we have a radius of convergence that is bigger than 0 but less than infinity, we're going to need to check to see if it converges at either endpoint. So let's do some examples. Let's say we want to know the radius of convergence in the interval of convergence for the series n equals 0 to infinity, -1 to the n, x to the 2n, over 2n factorial. Since we have a factorial in our terms, ratio test is probably the way to go. In all of these, you'll probably use the ratio or the root test to determine these things, because again, those 2 tests have a condition that tells us whether or not something converges or diverges at the end by taking the limit. All right, so put an n plus 1 everywhere for n. We get -1 to the n plus 1, x to the 2 times n plus 1 over 2 times n plus 1 factorial. And then in the denominator, we just have the nth term. The absolute values will take care of the negative ones because those will just end up being 1, so those go away. I really didn't need to leave the factorials here inside the absolute values because factorials are going to be positive. When we simplify, though, we do need the x's inside the absolute value bars because the x's might be negative. Although in this case, we only have even powers on the x's, so that won't matter there either. We get x to the 2n plus 2 because I have to distribute that 2 through the n plus 1 over x to the 2n. On bottom, we get 2n, or excuse me, for the second fraction, we get 2n factorial over 2n plus 2 factorial. Again, the 2 has to get distributed through the n plus 1. Simplifying now, when we subtract our exponents here, we just get x squared. And as notice here, I've lost my absolute value bars because I don't need them anymore because everything here is positive. Starting with 2n plus 2 factorial, remember it goes down by 1 each time. So we pull off the 2n plus 2, we've got to pull off another 2n plus 1 before we get to 2n factorial. It doesn't just skip from 2n plus 2 down to 2n. Okay? Factorial means we start at the number that's in the parentheses there and then go down by 1s each time until we get to 1. All right. So now our 2n factorials cancel. We're left with x squared over 2n plus 2 times 2n plus 1. Remember, our x here is fixed. So for a fixed x, this is just a number. These get bigger and bigger as n goes to infinity. So the limit's going to be 0 no matter what we plug in for x. That means that the radius of convergence here is going to be infinity because the series converges for all values of x. And that also means that our interval of convergence is minus infinity to infinity. Let's look at the radius and interval of convergence for the series n equals 0 to infinity. Negative 1 to the n plus 1 times x plus 4 to the n over 3 to the n. This one is set up pretty well for a root test because we have things raised to the nth power, so let's use it. Could use the ratio test as well. There's nothing wrong with it. Just since we have n power here, seems to be fairly straightforward to use the root test. So we'll do the limit as n goes to infinity of the nth root of the absolute value of the nth term. I'm just rewriting my root as a 1 over n power here. Here's my absolute value bars, and here's the nth term. The absolute value here will take care of this negative 1 to the n plus 1, because it'll always just be 1 then, so we can ignore that. 3 to the n to the 1 over n is just going to be a 3. X plus 4 to the n to the 1 over n will just be x plus 4. We still need absolute values, though, because x can be anything that we want, positives or negatives. And I want to make sure this turns out to be positive all the time, since we have absolute value bars. There are no n's here. All the n's went away, so this limit literally is just x plus 4 over 3. All right, we want this limit to be less than 1. So if we multiply both sides by 3, we'll get absolute value of x plus 4 is 3. We've solved for the absolute value piece here. We now have x minus some number is less than a value. That fits into that conclusion of the theorem we talked about before. This series is centered at negative 4. And we have absolute value of x minus negative 4. We want that absolute value to be less than 3, so the radius of convergence here is going to be 3. Since the series is centered at negative 4, we have to go 3 units below and 3 units above to figure out what the endpoints are. 3 units below takes us down to negative 7. 3 units above takes us up to negative 1. So the endpoints of the interval of convergence are negative 7 and negative 1. We need to check the convergence of that series at those endpoints. If we put in negative 7, we get negative 7 plus 4 to the nth power, or negative 3 to the n power. Our 3 to the n's will cancel. We'll get negative 1 to the n plus 1 times negative 1 to the n. Well, no matter what we plug in for n, one of them will make the power, or the negative 1 negative, because it'll be an odd power, and one of them will make the negative 1 positive 1, because it'll be to an even power. So in any case, we're always going to get -1 no matter what we plug in for n. So that series diverges by the nth term test for divergence. Likewise, if we put in -1, we get -1 plus 4 is 3 to the nth power. The 3 to the n's cancel, so we get the sum of just -1 to the n plus 1. So we get the series -1 plus 1, -1 plus 1, -1 plus 1. That series also diverges by the nth term test for divergence. And you should think about why that's true. Both of these series diverge for the same reason. Think about why that has to be the case. So in this case, we got the interval of convergence as the open interval, -7 to -1.